Yep. That's it, I think. Yeah. Yep. Right now we need to, oh no, be at the Zoom and finish this one and 100%. Yep. วันนี้มีกันบ้านไหมครับมีครับแน่นอนครับโอเคนี่ Saturday now, right? Somebody needs to be close. Same. What else? Yep. Let's see what happens. Scenario. Okay. Yep. We have to let's try. Okay. So this one. Right. So we're gonna use this one. What is the เรื่องอะไรนะครับเดี๋ยวครับผมกำลังเซตอยู่นะเดี๋ยวตอบให้ครับit's the right in what is that ส่วนกุหลาบclass attendance this one right in 604 in it's the right class attendance score oh yeah oh the wrong code okay yes okay เรื่องอะไรนะครับ F I L D sign เฟรา and then just stream how is that yep Okay. I'm not sure whether you
อาจารย์ครับ
เชิญครับ
ครับมีเพื่อนถามว่าเช็คชื่อผ่าน YouTube ได้ไหมครับพอดีเพื่อนแบบเข้าสู่ลำบากอะครับ
ได้ครับไม่เป็นปัญหาครับพิมพ์มามันมี2ช่องนะครับ YouTube นะครับมันจะมี YouTube ตรงๆกับกับจากซูไป YouTube ครับใช่ไหมครับ
ขอบคุณมากครับ
ครับคุณเลือกเอาเลยครับผมพยายามเปิดช่องทางให้คุณมากที่สุดว่าคุณจะได้สบายๆครับ close the microphone here okay all right and yeah good morning everybody welcome you to the SCI33205 yeah it's actually physics number 4 right we're gonna see what's going on so that we would not leave waste our time so much. We're gonna go ahead with our lecture notes immediately. All right. 511. Actually, to take care of to that. Okay. Not sure someone is waiting for. Oh yes. Okay. All right. This is the Zoom to YouTube. Yeah. We yes เช็คชื่อใน YouTube ได้ครับได้ครับได้ครับแคปเจอหน้าจอใน YouTube ส่งมาในไลน์กลุ่มด้วยเผื่อกันพลาดเผื่อการพลาดผมหาไม่เจอครับโอเคso here we have the okay still more 5 people yes still more 2 people one more กันพลนะผมได้รับอันนั้นแล้วครับแจ้งไปที่ครูเมื่อคืนแล้วนะครับ ก็ไม่รู้ว่าเขาพร้อมแก้ให้คุณแล้วหรือยังครับ แต่ว่าก็แจ้งให้คุณแล้วนะครับ
จะครับได้ที่1มาแล้วครับอาจารย์
เข้าใจครับคุณพิมพ์ชื่อโอเครู้สึกเป็นสุภาษิตนะครับตามสบายเลยครับผมไม่รู้ว่ามันจะกระตุกหรือเปล่านะเพราะว่าดูเหมือนว่ามันวิดเก็ตมันบอกว่าวิ่งแอร์เลอร์นะครับใน YouTube ครับแต่ว่า YouTube จะเป็นช่องที่เห็นหลายมุมมากที่สุดนะครับแล้วก็ถ้าเสียงใน YouTube ไม่ดีไม่มีอะไรก็แจ้งผมได้เลยครับโอเค let's continue our topic so that we would not waste so much time I want to go quickly there it's มีคนรออยู่ไม่เอ่ยไม่มีคนเข้านะครับถ้าผมอยู่ตรงนี้แล้วผมจะมองไม่ค่อยเห็นนะครับyes I have to share the screen วิรพัฒน์ share the screen right okay I hope that everything is fine the microphone should work perfectly, right? Okay. For M604, we arrive at the magnetic force of two conductors, right? Yeah. นะครับเอาจอนี้ขึ้นไปให้ด้วยนะครับ ที่ YouTube นะครับคุณจะได้เห็นนะครับYouTube มี2 อันนะครับจากซูมไปนะครับถ้ามัน YouTube ตรงๆมันกระตุกแต่ว่า YouTube ตรงๆเนี่ยรู้สึกว่ามันจะแม่นที่สุดนะครับคือภาพจะชัดที่สุดครับแต่มันจะมีกระตุกผมยังแก้ปัญหาเน็ตไม่ค่อยดีครับที่นี่มี 5G เฉพาะของ True เท่านั้นนะครับผมซื้อซิม AS มาด้วยนะครับแต่ว่ามันไม่เวิร์ก 5G นะมันขึ้นแค่ 4G นะครับที่นี่นะครับโอเคโอเค let's continue our story we arrive at the page 96, right? It's something about the magnetic force between two conductors, which is an extension to the typical the former topic, which is the force acted on the long straight copper wire, right? Or the conductor. Okay. So see now. Okay. Yes. This one will be a little bit more complicated. Okay. It includes something more. Okay, with respect to the former topic. In the previous topic we have only a single long straight copper wire, right? But right now we have both. We have two long straight copper wire, and of course each long straight each conductor can have two possibilities. Okay, two possible ways of current movement or flow, right? And the current movement plays also a significant role in the direction. โอเคครับ K นะครับพิมพ์นะครับin the direction K รู้สึกว่าเป็น K หรือเปล่ากัสซิดิตนะครับผมอยู่คุณดานผมเริ่มจำชื่อได้ครับโอเคplays the current movement or current direction in each conductor plays a significant role whether the force will be attractive force or the compelling force. Okay, the force that try to bring both conductors to be away from each other. Okay, the compelling force. Okay, and I would like to give first the introduction to this topic. It includes also the effect of the Biot-Savart formula. Okay, maybe you have seen earlier. Okay, everything that we have seen before. Okay, is going to be included more and more in the succeeding section, and especially this one. Okay, yeah. What happened? Okay, พิมพ์ชื่อกันมานะครับ Okay, yeah, we consider the two long straight copper wire. Okay, and we have one of that on the upper part. Okay, and ผมเดี๋ยวขออนุญาตต่อเมาส์ซ้ายดีกว่าครับเพื่อว่าจะได้ใช้งานอย่างคล่องแคล่วนะครับและชี้เมาส์ให้คุณนะครับทั้ง2ช่องนะครับ So right. Okay. Right. Do you have the upper conductor? Okay, it makes of the same type of material. the lower one as well, okay, according to the same color of the bar or the conductor you have seen here. And the one important thing that you need to pay attention is the symbol, okay, here, the dot symbol, as I have mentioned it earlier to you, okay. The dot one represents the head, okay, the front view of the arrow or of the vector, and the cross side, okay, represent the X side or the cross side represents the tail or the rear part of that arrow or of that vector, right? That's typical way in physics, okay. If we draw the arrow with those with that amount of arrows, okay, it's gonna be very complicated and it's not easy to understand, okay. This is the effect of the magnetic field, okay, the blue one or the cyan color of those dots and cross side represent the magnetic field lines that is induced by here. This is the magnetic field lines, as you have seen, represent the field line that is induced by this copper, this long straight copper wire, okay. This is what it can be said it's ampere law or Biot-Savart law, okay. Biot-Savart law will tell you how to get the magnitude of the induced magnetic field, okay, the strength, the B, okay. But the ampere law is involved both the right hand rule, okay. The right hand rule will give you the direction of the induced magnetic okay, the right hand rule, okay, if you lay your thumb according to the direction of the direction of the current movement, okay, you will get the direction in the direction from your remaining four fingers, and that will be direction of the induced magnetic field lines, okay. And of course, at the lower part, lower conductor, there will be magnetic field, okay, which is a distance, okay, from which is the result at the distance from the magnetic field caused by the lower conductor, okay. It's pointed or directed in this way, okay, out of the lecture note, okay, to us, but it's they write it in another different angle, so it's directed in this way, okay. And of course, from the topic that we have seen before, we use F equal ILB, right? You start first from the direction of vector L, right, which is the same direction as the current movement, okay. In the second, we are now considering the force, okay, that will happen on the upper at the upper conductor. In the first vector is in order to determine the force from the lower conductor, okay, the magnetic causes by the lower conductor, we have to use again the same expression FILB, okay, in order to determine the direction of the induced force, right? But B is the magnetic field from the lower one, okay. But the force is the force that will take place at the upper conductor. Okay. Internet ผมเป็นอะไรครับมัน security no we're gonna use ประภาวิทย์ครับไม่มีปัญหาประภาวิทย์เนี่ยซูมนะครับมันชอบเข้าของมหาลัยนะครับซึ่งมหาลัยมันไม่แรงครับ Okay, yes, the first vector is the vector L, right? The vector L, and of course the vector L is gonna be pointed in this direction, right? This is the vector L. Okay, according to the direction of the current movement, right? And yeah, this one, okay, the vector L. The second vector is the induced vector caused by the lower conductor, but here, okay, the B, the vector B that is pointing in this way, okay, and of course we can draw it right now. Vector B right here, right? Okay, that's the vector B, and then yeah, you have to curl or turn your four fingers, right, from vector L to vector B in this direction, and then you will get the outcome, which is the induced force caused by the magnetic field from the lower conductor right here. Okay, and that's the first force. Okay, we can get from the whole scenario, but actually there will be also a force, okay, exerted on the first conductor or the lower conductor as well, because these conductors can get the effect of the magnetic field from the upper conductor as well, okay, because there is current movement in the upper conductor, okay, and the upper conductor will generate the magnetic field line as well, and that field line will go and it will cross the lower conductor as well, okay. But first, if we draw everything, that will be difficult because everything will be complicated. So they just show only in this book, they just show only the force, okay, that happens at the upper conductor only. Okay, let's move to the next one, okay, which is the full version. Okay, you understand the cross and dot symbol, right? It's the tail and the front view of the magnetic field line. Okay, now let's consider the that's the same thing. You have the sorry for that. You have it's the same kind of what we have seen before. Okay, this figure has no big difference from the previous figure. And I don't understand why we could not get good internet from this one. Okay, anyway, don't worry about it. We go ahead with, okay, this figure has nothing to explain more. It's the same thing, okay. When they throw away the box actually doesn't happen, okay. They just put the box into this so that you can see the head and the tail of the magnetic field line, okay, so that you can understand. But actually, it can also be seen as this figure, the figure 34, okay, it's not different at all. And the force will take place in any location along the length of the conductor along the the upper conductor. Okay, the force will happen everywhere. Okay, as soon as you have magnetic field that is crossing the upper conductor, okay, the force will take place everywhere. Now let's move to the lower the next figure in figure 44. Okay, it's taken from a different book. Okay, you may see some different notation, but actually it represents the same thing. All right. So right. Okay. Yeah. This is the figure that represent the same thing. Okay, the same idea. The force happened at the two parallel conductors. Okay, but this one, if we get into the detail, this will represent the force that happens to the upper conductor as well. Okay, but okay, now the currents move in both conductors in the same direction. Okay, in the same way, from left to right. From okay, the upper conductor is denoted by number 1, and the lower conductor is denoted by number 2. Okay, the first and the second conductor. Okay, simply speaking, and it can be possible that the designer or the person who controls all of this stuff will let the current flow with different value. Okay, that's why they say capital I with the subscript number 1, and here the current I, okay, with subscript number 2. Okay, it can be possible. Okay, it can be different value, and the distance between those two conductors is the D. Okay, in the magnetic field line that is significant. Okay, the important magnetic field line is the green one. Okay, is represented by the green circle here, and at this location, the dots, the black dot here. Okay, that's the position which is important. Okay, which is vital to us. Sorry, we're gonna make the analysis of the force field that will take place at this point. Okay, that's this at this dot line. Of course, according to the right-hand rule, okay, the green one represents the magnetic field line caused by the lower conductor or the second conductor. Okay, according to the right-hand rule, you can see that the magnetic field at the black dot position, okay, is gonna be directed out of the plane or in this direction. Okay, but they cannot draw it in 2D, otherwise it's not it doesn't include, so it doesn't include enough information. Okay, that's why they draw it in a different angle. Okay, this is the magnetic field. Okay, it's magnetic field strength actually, and they just say the subscript number 2. Do you know why? Why don't they say B with subscript 1. Okay, this is the magnetic field at the location of the first conductor. They should use the B with subscript number 1, right? But it's not the case because this B, okay, the magnetic field here is caused by the lower conductor. Okay, it's the lower conductor. It's the second conductor, so that's why they write down here the subscript number 2. Okay, and we are gonna analyze, okay, or find the direction again. Of course, we are gonna use the same formula if ILB. okay ผมจะพูดไปเรื่อยๆนะครับจะใช้สูตรเนี่ยไปเรื่อยๆจนคุณซึมซับไปเองครับถ้าใครก็อย่าเพิ่งเบื่อไปก่อนนะครับใครที่ฟังแล้วไม่ค่อยเข้าใจก็มันก็ไม่มีอะไรนะครับมันก็มีแค่นี้นะครับ okay, we use the typical formula FILB in order to find the direction first, right? Of course, the vector L in this scenario is gonna be in the same direction as the vector in the same direction as the current, right? The current okay, the current I1, okay, it's we say that we are considering the length of the conductor at the section of L only. Okay, let's say the length of this conductor is L. Okay, it's the written style of the L letter, and yeah, nothing wrong, right? In the next vector, okay, the second vector to us is the vector B, right? We need to draw how the B vector points. Here we have the vector B, and it's in this way, right? And yeah, you have to turn your finger, okay, your 4 fingers from the vector L to vector B like this, and the outcome, the result will be the direction given by your thumb. Okay, and this will be the induced force direction. Okay, and let's say this is the first force. Okay, the force that happens to the first conductor, the upper conductor. Okay, it's not too difficult, right? Okay, so now we go further to okay, you get to know how to determine the direction of the induced force already, right? But in physics, as I often say, there are 2 things. Okay, apart from the direction, we have to also take care of the magnitude, right? So it's time now to find how strong is the force. Okay, so the force of interest to us in that in the former page is F number 1, right? And from the basic formula we have seen in the previous top. Oh, sorry, it's not the version. It's the scalar version. So it's I L B psi theta, right? Or psi phi, up to you. Okay, and yeah, we have to get into the detail. Which F we are considering? It's the F that take place at the upper conductor. So we need to write down the number 1 as the subscript for the force in this case. Okay, and yep. The detail for the first variable, force, okay, induced force, is already defined, right? Now let's move to the second variable, which is the variable I, right? Where is that? What I should we deliver to this formula? Of course, I should be related to the variable L, right? Which is the length of the connector that we are looking at the current. Okay, so L should be the same one as the I, right? The I. So yeah, the I should be the L, vector L should be related to I here, right? And this I is I with subscript 1. Okay, so we write down here I with subscript 1. Okay, and L is only the magnitude, right? In this scenario, in this figure, it just simply say that we consider the same length of both conductors. So variable L will be the same for those two conductors. So we don't have L with subscript 1, L with subscript 2. Okay, simply L, okay, without any subscript. And B, let's talk about B in this scenario at figure 44. Okay, what about L? What does L mean? What does L mean in this case? Well, if we refer to the former case, when we would like to determine the direction, we just curve our four fingers from L to B, right? And ที่นี่มันจะใหญ่ไปนะครับเล็กหน่อยthe B that is significant to us is the B is the magnetic field caused by the second conductor, right? So vector B here is the one that is caused by the conductor here I2, right? So the second conductor. So this B should have the subscript number 2. Okay, so that's why we can say it's B with subscript 2. But now we move to the fourth variable. Okay, fourth term, which is psi theta, and of course the important variable for us is going to be theta, right? And you can see that theta in this scenario is the angle here is actually what color should I? The green one. Okay, the angle here is right angle, right? So this one will be will give you theta of phi as 90 degree. Okay, and you can put 90 degrees to this variable, right? And nothing will be important for us anymore because psi of 90 degree is gonna remain or yield number 1, right? So that's the reason why they get the simple expression in equation number 40. Okay, only I1, L, and B2. Okay, so with this analysis we get the simple result, which is I1 and LB2. Okay, I have delivered the detail already to you, right? How we arrive at the equation number 40, but it's not the final result yet. Okay, we have to go further The further the additional analysis is that what is the magnitude of magnetic field B2? Okay, what is the value of B2 if we don't want the result like this? Okay, we want to really a deep detail on that, and we're gonna go back again to the figure number 44, and we will try to find the magnitude of vector B2 in this one. Okay, and you can see that B2 is the magnetic field caused by the lower conductor, right? The conductor, the second conductor. So we need to borrow the idea or the content from B.O. Sawat's formula, which is นักเรียนได้คะแนนเท่าไหร่คะไม่ได้เท่าไหร่คะให้Okay, and yeah, we need to borrow the idea from B.O. Sawat's formula, which is the formal topic is the formal topic known as the magnetic field caused by the long straight copper wire, right? So you just brought the detail in the following page, okay? But I can also write down the B.O. Sawat formula again for this scenario. B2, right, is going to be mu0I. If you can remember this one, okay, from the midterm exam or midterm test, mu0 and 4 pi r, right? But r in this scenario is gonna be the distance, okay, the distance where both conductors are separated from each other. It's 4 pi d, right, instead of r, right? We get B2, which is mu0I and 4 pi d. Oh, sorry, it's 2 pi, not 4. I'm stupid. 2 pi d, right? Don't get confused with that, because I am often aware that mu0 is 4 pi times 10 raised to -7, right? So that's why 2 pi or 4 pi, but 4 pi is inside mu0, okay? And yeah, I've got already the explicit sorry. We need to specify also the current, right? And the current in this one, okay, from the B.O. Sawat formula is the current related to this one, right? Related to the second conductor or the lower conductor, right? So this I should be the current there, okay, the current here, okay. So we get I2 actually to the B.O. Sawat formula. So we need to write down number 2 as a subscript in the B.O. Sawat ratio fraction there. Okay, let's move to the slide. Okay, I have already given the explanation why we arrive at equation number 41, right, from the figure. So if you have any unclear issue, just let me know. And then we will substitute 41 into 40, okay, in a straightforward manner. And of course, you can see that IRB, right? You put the value of B into this one, right? What happened? You put the value of B into 40 and equation number 40, and you arrange something. Okay, you move the เดี๋ยวขอเช็คดูก่อนนะว่าสูบมีใครขอเข้าอีกไหมเดี๋ยวผมไม่ได้กดรับเขาคุณก็จะแย่นะครับโอเคครับไม่มีแล้วนะครับโอเคที่ซูมอยู่มัน10 กว่าคนนะครับโอเคlet's go to okay continue our story yep we need to arrange everything in a tidy way. Okay, we need to manipulate everything. We move all the terms at the upper part at the numerator position together. So we get a good result to that. And the result will be the second equality in equation number 42. Okay, it's mu0 I1 I2. Okay, now we have both currents. Okay, and L. Okay, L is the length of both conductors that we are taking a look at. Okay, and 2 pi d. 2 pi is a constant, and d is the distance where the distance when both conductors are separated from each other. Okay, all right, and that's the first force that happens or exerted on the first conductor, right? And you may have a question: what about the force induced at the second conductor? So what should it be? All right. So I may not go completely into the detail how we arrive at the expression of the magnitude for the induced force at the second conductor. Okay, but you just borrow the idea before. Okay, how you get the force from the upper conductor. Okay, in the same way. Okay, and you can derive it in you get the force, the amount of force exerted on the second conductor as well. But if you want, I can write it in the detail. It's no problem. Why we get equation number 43. Okay, ทำไมเราได้สมการ43ครับมันก็ไม่ยากนะครับ Okay, at the second conductors, we would have the amount of force. Okay, if F2, right, at the second conductor will be ILB as well, right? But we don't need to write down sine theta anymore because the angle is 90 degrees, right? So we don't pay attention to the sine theta term. It's simply number 1. But which I, in this case, okay, if you take a look at the force, this is number 1 and this is number 2, right? The force that will happen at the second conductor will be the current, will be the result from the current itself, okay, which is I2, okay, and L is the same thing, right? Because that's the portion of the conductor or how long the conductor, which will be the same amount for both conductors. So L in this one will be the current I. Okay, the first variable will be I with subscript number 2, right? Because we are considering the current. Because we consider the current at the second conductor, so we write down the subscript number 2. And what about B? B is the magnetic field from the first conductor, so we need to write down B1, right? Because B is the magnetic field line from the around the first conductor, but it just passed through the second conductor, so it's the magnetic field from the first conductor. Okay, but if you go into the detail, what is the exact expression of the magnetic field from the first conductor will follow the same idea from the Biot-Savart formula, which is mu 0 I and 2 pi r, right? But r here is d, right? In this scenario, we just write down d. And which I in this one, okay, in B1. So it should be the result from I1, okay. So we write down here the subscript I1, okay. And you put now you put B1 into the result or the expression of F2, okay, because it's B1, right? And when you leave it into the upper equation, you will get the result in equation 43 easily, okay, with the same way as 42, okay, a little bit manipulation. Okay, we can see that finally the results from both conductors will be the same, okay. All two values here are equal to each other, so it's the same thing, okay. Mu 0 I1 I2 L and 2 pi d, okay. So we can conclude that F1 is equal to F2, right? And this, if you have time and you think more, okay, think of that, you will see that this correspond to the Newton's third law, right? Action force is equal to the action force, right? That's the third Newton's third law, right? And one thing you may forget to mention is that maybe you have already realized that the thing is that the directions of the currents in figure 44 or equation 43, okay, or sorry, in figure 43 or in figure 42, what do you see? The directions of both currents are in the same way, okay, are the same. So in a bigger scale, okay, in a bigger view, we will conclude that when the when the currents flow or go in the same direction, we will get the forces that are pointed to each other, okay. So simply speaking, it's the attractive force, okay. Those are two attractive forces, okay, and the amount or the magnitude are the same, okay. Is there any figure to show whether it's yeah, on page 101, right? โอ้มี190 หน้าครับ yeah, you can see that the same direction of the current leads to will deliver the attractive forces to you, right? And what about the results if we have the current flowing in the opposite direction, okay, in different direction? Okay, yeah, in the former scenario we have the parallel conductor. I may not write down it properly. The currents flow in the same direction, and we get the attractive force, right? This is F2, okay. F2 is pointing up, and F1 is pointing down. Okay, that's the attractive force. Okay, the force that try to bring those two conductors to be close to each other. Okay, to be close to each other. And what happens if we have again the same pair of conductor, but right now we let the current flow. Let's say the first one flow from left to right, and the second one conductor has the current flowing from right to left. Okay, in the opposite direction. You can imply also when the above conductor has the current from right to left, and the lower one has the current from left to right. Okay, but anyway, both currents are in the opposite direction. What is going on? What is going to happen to this case? After you make the analysis by using the right-hand rule, the induced magnetic field line, and you use the FILB with vector version, and you use your right hand again, you will find that the force that take place to the at the first conductor is going to be F1 that will be pointed out of the lower conductor. Okay, saying the force that happens to the lower conductor or the second conductor will be down. Okay, will be downward like this. Okay, so we can conclude that when both currents have different directions, okay, either from left to right or right to left, but both currents have the opposite direction, we will get the repelling forces. Okay, the force that try to separate both conductors from each other. Okay, and we call repelling forces. Okay, ก็คือแรงแบบผลักกันนะครับ Okay, if you don't completely understand or you want to better vision to that thing, okay, we can take a look at figure 45, okay, which is taken from a book in the bachelor degree level. It will give you more the clearer vision about that, what happened. Okay, before we have formally we have the single conductor, right? And let's say the current flows from the lower part to the upper part of that conductor, and you just apply your time direction, and you get the results of the magnetic field by using your right hand rule. Right, the 4 fingers will give you direction of the induced magnetic field, right? And there is no force happening at all to this scenario, right? We won't talk about the force at all, because we just simply consider the Biot-Savart formula, B equals mu0 I divided by 2 pi r, right? There is no force at all. But in the more in the next topic, that is the topic right now, the current topic to us. We have 2 conductors, right? And again, when we let the current whether flow in the same way, okay, this one, okay, the current flows in the same direction, okay, from the upper part to the from the lower part to the upper part, right? They flow upward like this. After you use the analysis by using after you make the analysis by using your right hand, you can see that you get the attractive forces, okay, with the same amount, okay, with the same magnitude, but it's attractive forces, okay, the force that try to bring those 2 conductors to be close to each other. And let's move to the right figure, okay, right sub-figure here. We have the current flowing in the opposite direction, okay, whether up or down, okay, but both currents are in the different direction, in the opposite direction, okay. After you make the right hand rule, and after you use the right hand rule, you will find that the outcome or the output of the force will be the repelling forces. Okay, the force that try to keep those two conductors far away from each other. Okay, and that's it. That's the whole story. You can get the relationship to the former topic. Okay, in before in the midterm exam. Okay, let's apply all the stuff we have seen before to one of the problems. It's example taken from the book number 2, example 8. There are two wires, and each has the weight per unit. Oh my God, what is going on? Weight per unit length. Okay, just keep that. Okay, we have never heard before weight per unit length. Okay, they say weight per unit length of 10 raised to the negative 4. Okay, it's very tiny. It's 0.1. It's not gram, right? It's 100 micronewton, something like it's very tiny. Newton per meter is the weight per length. Okay, let's say if you have a connector like this, and if you cut it, okay, this connector might be so long, but if you cut it for only 1 meter, okay, let's say this is 1 meter, you will get the amount of weight for only this portion, like 10 raised to negative 4 Newton. Okay, and that's the meaning of the weight per unit length. Okay, you cut it for only 1 meter, you will get that amount of weight. Okay, for such type of conductor. I don't know which material they are made of. Okay, assume the wire carry the currents that are equal in magnitude. Okay, that's it. Means from this information that I1 and I2 will be the same, right? Let's say we have two conductors like this, and we let the current flow like this. Okay, and I don't know they will be in the same direction or, but I from the first conductor and I in the second conductor have the same magnitude. Okay, let's say I1 equal I2, and it's equal, simply speaking, I. Okay, without any subscript at all. Okay, it can be 10 or 5 ampere up to reality, and opposite in direction. Okay, they say opposite in direction. So when I draw I1 pointing from left to right, we need to draw I2 in the opposite way, which is from right to left. Okay, the y's are 0.1 apart. What information do they give us? It means they say the distance between those two connectors is 0.1 meter. Okay, and the sum of the magnetic force and gravitational force on the upper y is 0. Well, what happens? We didn't consider the gravitational force at all in the previous configuration, in the previous figure, right? But anyway, it's not too difficult. Yeah, it's เดี๋ยวขอแคปเจอร์หน้าจอไว้ครับเดี๋ยวเพื่อตอนเลิกแล้วผมหาชื่อคุณไม่เจอนะว่าคุณมากันจริงๆครับไม่งั้นต้องเดือดร้อนให้คุณครับหน้าจอกันอีกครับ Okay, they include also the effect of the gravitational force, which is the weight, right? Yeah. Okay. let me write down, okay, or open a new figure. Yeah, we will take a look at first couple Y, right? In this is the first connector, right? Connector number 1, and this will be the connector number 2, okay, and it has the same length. They say it has current moving in the opposite direction. This one from left to right, and this one from right to left, okay, in the opposite direction already. And they say the sum of the magnetic force and gravitational force remain 0 at the upper connector. So we have to write down the gravitational force, right? The W, right? The mass, the weight of the first connector, right? Sorry for that. Right, and there will be also the induced magnetic force, right? According to the topic, force caused by two parallel conductors. But what direction of the induced force should be? Okay, what direction should the induced force be in at the upper conductor or the first conductor? It should be down or up. Okay, it should be pointed downward or up or upward. What do you think? Based on the idea that we have seen before, it should be downward or up. There are two reasons behind that. Okay, if you can remember what we have seen before, what time is that? Only กี่โมงแล้ว? It's 9:42, right? It's not yet. ผมต้องปล่อยคุณที่ 9:50 หรือเปล่าใช่ป่ะ 10 ใช่ไหมครับ 10:10 เนาะที่เราเลิกกันครับ yes, I need to leave you at 9:50, which is 8 minutes remaining. Okay, two reasons can be inferred from can be inferred to determine the possible direction of the magnetic force. Okay, if you can remember the story that I have said before, or if you can remember this figure, when we have the different directions to the currents, we're going to have the repelling force, right? The force that try to make both conductors away from each other. So with that case, we can now get the direction of the magnetic field FB. Okay, sorry, F1. Okay, F number 1, which is the force exerted on the first conductor. Okay, if you cannot remember what we said about whether the current will flow in the same direction or opposite direction, we will get repelling force or attractive force. It doesn't matter. But the example said that there is equilibrium, right? The magnetic force and the gravitational force can be combined, and the result is 0. So it means that we are in the equilibrium state. Okay, the summation of the force is 0, so the conductor can stay easily. Okay, and now let's move to the only 6 minutes. Let's move to the question. Find the current in the wires. Okay, neglect Earth's magnetic field. Okay, we don't pay attention to the Earth's magnetic field, which is around 50 microtesla. Okay, we are gonna find the currents. Okay, let's say same magnitude, right? So we would say that the current is denoted by I. Okay, I also at the second connector, but we don't need to take care of the second connector at all because everything important is included in the first connector, right? And in order to find the currents, we have to use the typical formula, which is equation number 42 and 43, right? 42 and 43 give us mu0 I L divided by 2 pi d, right? So we are gonna use that expression to this example, right? I need to go quickly so that we can finish this example. F2, oh sorry, F1. F1 is mu0 I1 I2 and L, right, divided by 2 pi d, right? Pi d is the distance, the separating distance between those two conductors. But as we know, I1 and I2 are the same, right? Which is simply I. So we're gonna have this expression as mu0 I square and L, right, divided by 2 pi d. But the question is, what is the value of I? So we have to manipulate everything, and we need to find I. So we would get the result as F and 2 pi d, right? And sorry for that, the ugly parenthesis, sorry for that. And mu0 L, right? But is in the square root. But what we still don't know is F1, or simply speaking F, okay? Because the force will be the same. From the Newton's law, the first law, Newton's first law say that the summation is summation of F. Oh, sorry. Summation of F is 0. We still have 3 minutes. Okay, and it means that W is equal to F1 or F, right? And of course, the weight of the conductor can be computed by what they have provided is the mass per the weight per length, right, which is mg, right? W is mg, right? Okay, mg equal F1. Okay, so now we will substitute mg by F1. Okay, m is the mass of the conductor with that length. Okay, and it's again 2 pi d and divided by mu0 and L, right? And the important thing is we substitute F1 by mg, right? The mass of that conductor and the gravitational acceleration on Earth. But if we manipulate this expression, well, we will see that you can see that there is the weight per length, right, which is square root of 2 pi d divided by mu0, and we have a term right here, mg, which is weight per length, right? And because the problem, the example has provided the value of weight per length, so we have to use that amount easily. So we put the number right now 2 pi and d. What is d? It's 0.1, right? 0.1 meter, 10 centimeter actually, but they just simply say it in the SI scale already. So 0.1 meter and divided by mu0. Mu0 is 4 pi times 10 is to -7, right? And the L is the length of the conductor right now. Or the length is not needed because they just provide the value in terms of weight per length already, right? So we need to remove this one. Okay, and we will simply write down the amount right here, which is the weight per length. Okay, this is weight per length. Oh. Okay, so what they have provided is 10 raised to -4, right? So it's 10 raised to -4 Newton per meter, right? It's right there. So we put everything into the calculator. Okay, you will get 50 already. You will get the result. Okay, which is 7.07 0.07 ampere. Okay, and that's it for the first example in force exerted on two parallel conductors. Okay, I need to leave the lecture right now. Okay, so that you can have 20 minutes break. So the homework for today includes also the former topic, which is FILB. Okay, the homework is FILB or this one. Okay, you can choose both topics. จะเห็นว่าคะแนนการบ้านสำคัญครับ you can choose the FILB, okay, force exerted on a single conductor or the force exerted on two parallel conductors, equation 42 and 43. If you have any questions, just let me know. If not, we're going to leave and see you next week. Bye bye ครับ สวัสดีครับ